I'm recording this. I think I should have recorded the PV energy production, but anyway, now let's record the domestic hot water production with F chart. If you remember, you don't have F chart there. It's not, if you type F chart, it doesn't work. You have to browse it in your computer. It's in my PC, local disk, and we have F chart demo. Do you have it? Mm-hmm. Okay, so it's there. And then you can click here. We click OK. And this is what we have from the beginning. You see that by default, we have the pool heating system. Okay, so by default, when you open the chart, the first option is to heating up a pool. It's I mean, solar energy is the perfect energy to heat up the pool. I mean, solar collectors, not the PV panels, but the solar collectors. But if you don't have a pool in your building, we don't need to use this option. So we have to go to the system. Well, first we have to go to preferences. We have English units and economics on. I'm going to turn this off. In system, we have two options. We have the active domestic hot water. This is just for hot water. And this is the water storage and domestic hot water. So we have hot water and we can help the heating system. So we're going to do both, okay? So the first thing, it's mandatory, and at least this is what I'm requesting for this exercise. You have to deal with the domestic hot water. So if you click here, let's do this very quickly. I have explained that before on another video, but so I'm not going to explain all the options that we have here because I already did it. So location, that's the first thing we have to change. In this demo, we can select the city, but we can select the northeast of the United States. Yeah, so this is where we are, kind of. Water volume to collector area, we can keep 2 gallons per square feet. So that's the size or the volume of the water tank. The fuel, select gas, because in the Revit file, by default, we have electricity for cooling and gas for heating. Okay, so let's keep the fuel gas. Then the efficiency of fuel is 70%. It's quite low, but okay, let's do that. And this is the important thing, the daily hot water usage. By default, we have 80 gallons. Let's find out daily hot water in residential building. In a residential buildings, hot water consumption per occupants. Okay, so here we have hotels, houses and flats, liters per day and per occupant, and gallons per day. Okay, so we are talking about gallons. In houses and flats, we have 20 to 35. It's quite high. In hospitals, for sure, we need a lot of hot water. Schools, if we have showers, and we can assume that in schools we can have showers, it's 25, but in the office buildings we have only 5 gallons per day. Okay, so that's the first thing that you have to basically, if we have showers, we need a lot of in houses, hotels, schools. If we have showers, and hospitals, we have a lot of demand. So for houses and flats, it's per occupant, it's 20 to 35 gallons. So the first thing, how many people in your house?
I think it was
5 or 6. Let's say 6 times 20 to 35. Let's say 30. 6 times 30, it's 180. Okay. So that's the first thing we have to do. The daily hot water usage. is gallons per people. So if it's 180, so let's type 180 gallons. And then the water set temperature, it's 140. That's mandatory because we have to kill the bacteria and all that stuff. The environmental temperature, that's relevant. If it's 68, that means that our heating, that our tank is in a heated space. I know that in some the mechanical room, I don't know, when I was working with you, sometimes it was heated, sometimes it wasn't heated. So what they recommend is to place the water tank in a heated space. So 68 Fahrenheit is comfort temperature, so that means that it's heated. If we have the water tank outdoors, we lose a lot of energy. It doesn't make sense. At least it's in a mechanical room. And if the mechanical room is inside the house itself, even if it's unheated, it will take the heat from the rest of the house. So it won't be far from 68. But this is relevant. If we reduce this temperature, the efficiency of the panel will go down. This is the thermal insulation of the storage tank, of the water tank. We need thermal insulation around it. If we buy a commercial water tank, it's insulated. So 7.6, we can keep that. And that's it. Okay, so basically the most important thing is the daily hot water usage. That depends on the type of the building and number of people. Then here we have the number of collectors. The collector panel area, 20 square feet is 2 square meters. Yeah, so most of collectors are like this. So we can, and then this is the that's the efficiency of the collector, 0.7, 70% efficiency. It's quite good. Remember that the efficiency of PV panels is around 10, 12% maximum. Okay, so here we are talking about 70, 80% of efficiency. So this is a flat plane collector, probably heat pipe, like the ones that we have in this building. They can get up to 80, 85% efficiency, but this is around 70 to 75%. The slope, if you put your panels on the same roof, it will be 30 degrees. This azimuth south is 0. It's different than in PV watts. Okay, so here we have 0 azimuth. And the rest of the things, it depends on the fluid and depends on the specifications of the panel. We can keep this. So that's it. This is only 2 panels. 2 panels is not going to be enough, but let's run and calculate. And this is it. Okay. So what we have to look is the F value. So that's why we call this F chart, because the relevant parameter is this F value. And this F value, the yearly, okay, so here we have the year, it has to be above 0.6 or 60%. So now it's 0.15. So we are far. What do we have to do? We have to place more PV panels, PV solar collectors. Let's say 10. Let's calculate again. And now we are getting there. It's 58%. I think with one more solar collector, it will be enough. Yeah. Okay. So that is the minimum 60% of the total energy for domestic hot water. It would be the minimum amount of solar collectors that we have to include in our site. So that means that we have 11 solar collectors, and each collector is 20 square feet. So we have like 220 square feet. Here. So that means that if you are dealing with a roof like that, we need, hello, Paul. Is it?
No.
No. It was running a few minutes ago.
Die. He's out of 36, but.
Okay, so if we want this to be the zero energy building, we need like 220 square feet of solar collectors. And what was the area of PV panels? 550 square feet of PV panels. Okay, so now we have to figure out how we can place all that stuff. Okay, but this is what we need for the electricity, and this is the domestic hot water. Is this a zero energy building? Well, we're not taking into account the heating. Okay, so for the heating, it's gas. We have exceeded the electricity production, the electric production, but it doesn't mean that we can use that electricity to heat up the building. So that will be the first option. Okay, so here we have this for domestic hot water, and then PV panels. This is for electricity. In electricity, we include everything. We include lighting, power, and cooling. But in solar collectors, in this option, we only include the domestic hot water. So that would be option one. We can have option two. And option two, it's more complicated. It can be more effective because we can include the domestic hot water and heating. So I have to go to system, and system is, let's say, the third one, water storage and domestic hot water. So we are in the northeast. The water volume collector area, it's around 2, it can be 1.82, so we can keep that. This is the building UA. Okay, let's talk about this later. We have the water, daily hot water usage. According to this, it was 108.80 gallons per day. Okay. Water set temperature is the same, environmental temperature is the same. And what is this? What is UA? That's UA, so that's the U average of the building multiplied by the area of the envelope. Okay, so what is this? It's the U average of the building. So in the building, we have roofs, walls, windows, and floors. If the U value of the roof is 50, the U value of the wall is 40, or the R value, sorry. The R value of the floor is around 20. And then we have the R value of the window. We usually don't have the R value of the window, but we have the U value. So what's the U value that we have used? I'm sure that if I look at your project, I will find out. Will I? Where's the window catalog? Oh, it's here. Okay, good. So here, the U value, it's a 0.17. We have different for winter night and summer day. Okay, but it's a 0.17. That's the U value of the window that you have selected. Okay, so the U value of this window is 0.17. What's the U value of the roof? It's 1 divided by 50. So this is 1 divided by 50. It's 0.02. The U value of the wall, it's going to be very similar. 1 divided by 40. It's 0.025. And the U value of the floor is 1 divided by 20. It's 0.05. Okay. So what's the average, or what is this? We can say that this is the U value of the wall times the area of the wall, plus the U value of the roof times the area of the roof, plus the U value of the floor times the area of the floor, plus the U value of the window times the area of the window. Okay, so this is what that concept of UA means. Okay, so we have to add up the U value of different elements multiplied times the area of each element. So I don't know. I'm sure that you know your the area of the envelope, the roof, the, I don't know if you have it somewhere. You have the U value, but we have the window to wall ratio. Okay. Anyway, it takes a little, but let's say that we have the walls, the U value of the walls is 0.025 times, going to make it up, 800 plus the U value of the roof. Is 0.02 times 1,000 plus the U value of the floor, 0.05 times 1,000 plus the U value of the window, which is 0.17 times, let's say, 500. Okay, so if I do this, I have to multiply everything. So let's point 25 times 800. This is 20 plus 0.02 times 1,000 is 20 plus 0.05 times 1,000 is 50 plus 0.17 times 500, 0.17 times 500. This is 85. Okay, so 85 plus 19 is 900. 175. Okay, so that's what I have to type here. The UA is 175. So that's the UA of this. I don't know if those numbers are correct, the areas. You have to do it with your, but you don't have to. I mean, if you meet the passive house standards, you can take this 50, 40. Well, we need the window 20 because this is the common passive house standards. So that's all we need. Okay, so we have the daily hot water usage, and the building UA is the heating load. Okay, because that's the when we want to calculate the heating load, is the U value times the area times indoor minus outdoor temperature. The indoor minus outdoor temperature, it depends on the climate. So we have selected northeast. So the system knows what the difference of the temperature difference is between indoors and outdoors. And this is the information about the building. This is the material that we have used for the building, and that's the area, the shape of the building. So with all this, the system has all the information it needs. So now the number of collector panels, let's try 10 at the beginning, see what happens. We don't touch this because it's the same collector area, the same slope, 30 degrees, the same efficiency. So let's plot, calculate. And now with this, we are, okay. So the F value, it's much lower. It was above 0.6, now it's 0.4 because we have added heating load. Okay, but by increasing this, if we type 15 and calculate again, we are, but now we have to be careful with that. When we surpass this value 1, we can have issues with overheating. Okay, so we have to be careful with that. Basically, in January and in December, we have like 15, 20% of the energy that we need. Okay, so that means that by using this, we can reduce the heating load by 15 or 20% in winter, which is a lot. Okay, so that means that in this here, if this is the gas consumption in January, so we can reduce this 15-20% with all these elements that we have used. The F value, it's more than 1 in summer, because in summer we don't have any heating demand. We have a hot water demand because that's steady throughout the year, but the heating, we don't have any heating in July and August. But we can say, okay, let's put like 30 panels. Oh. Okay, so we increase in winter, we go up to 35% of the needs, but that means that it's dangerous and we have overheating. So if we have a pool and we can we can allocate all this energy into the swimming pool, that's good. But if we don't have a swimming pool, or if we don't have a way to get rid of this excess of energy, that will harm the system. It will burst because of the overheating. So be careful with placing a lot of panels, because we want free energy in winter. We have to think what we do with that energy in summer. And the only way to get rid of that energy is to have an energy sink. An energy sink, it's a place in which we can move the energy away, and that's a swimming pool. We need a huge mass of water to heat up that energy. Okay, if you don't have a swimming pool, I recommend you, I think 15 was good enough. Yeah, we have a couple of months, June, July, or July and August. No, it's June and July, in which we have a risk of overheating, but we can handle that. I mean, we can increase the size of the water tank, or, well, we can do something. And not running water is not the option, okay? Even if we don't run water, we have, the system is at risk. So it's not in winter, in summer, I'm not using the solar collectors. No, only it's the other way around. You have to use the solar collectors a lot because you have to move that energy, that excess of energy, to somewhere else. So what's the outcome of this? The outcome of this is that I think in plot, we have parametric plot, monthly plot, sorry. And here we can select different things. If you select F and plot it, you see that, here we see graphically the amount of energy that we save. Okay, so in January, we have up to 20% of the energy that we need, of the heating energy that we need. And in June, July, we have 100%. And even in May and September, we are very close to 100% of all the energy that we need. So that's the first plot. We can plot the heat in domestic hot water. Let's see what happens here. No problem. Okay, so that's it. That's the heat and that's the domestic hot water. That's interesting because this is the demand. We have, this is the domestic hot water demand, which is the same throughout the year because we use, if we wash our dishes, if we wash our hands, if we have showered, we have the same energy consumption. It depends on the number of days. In February, it drops because we only have 28 days, okay? But the rest of the year, the energy demand is steady. That's the energy demand of heating. And this is consistent with the Revit chart. Okay, so we have the same shape. We don't have any energy demand in June, July, and August. And this is what happens here in June, July, and August. We don't have any energy demand in heating, and the peak is in January and December. Okay, so that's the information that we need. The blue line is the same information that we can get in Revit. In Revit, we don't have information about domestic hot water. Here we do have information about that. And then, is there any other monthly plot that we can use? The auxiliary. Okay, that's interesting. So that's the auxiliary energy that we need. Okay. So when we don't have enough in June, July, and August, we don't need any auxiliary energy. But the rest of the months, we do need the energy that we can't have from the system, from the solar collectors. So here we have information about the energy, the heating energy that we need. And this information is about the auxiliary energy that we need, the part of the heating system that we can't cover with our solar collector. Okay, so if we go for this second option, we have 15 panels times 20. So that means that we need 300 square feet of panels or solar collectors. So here we have like 300 square feet. So with this 300 square feet, we can paste the we can paste either this or that, either the table or the graphic. Let's paste the table. That's the thermal output. So the relevant thing is the F value. So that's what we get with the solar collectors. Okay, so we can have an arrow. So with this amount of solar collectors, that's the outcome. We have up to 20% of the energy demand in winter, 100% in summer. And then with the electricity, with the PV panels, we will have this. Well, with the PV panels, we have this. This is the production and this is the demand. If they are at the same scale, that's important. We should see that, well, we have calculated that we had more energy production than energy demand. But it's important to get the same scale for both charts. Okay. So that's it. We have already done this. We have to test the passive house standards. You haven't done it yet. I think Caitlin did it last week. Yep. So that's what we need. We need to test our peak power demand for cooling and heating. We have to check the requirements for peak heating and cooling in the passive house standards. I remember that we did this with Caitlin last week. So we are far from meeting the peak cooling power. It's 26 and it should be 3. So the cooling power, it's really difficult to meet the peak cooling load. But we were good with the annual heating and cooling demand. So we were almost there in heating, 6.3 versus 6.2. And we had a very low yearly cooling demand, 1 versus 10. So that's these passive house requirements. They are kind of, it's very difficult to meet the peak cooling load. Basically, what they are telling us is that we shouldn't have any windows. But the fact is that we do have windows. So I think if we can persuade people, if we want to get this certificate, we can see that, okay, yes, we have a lot of, we have a high peak cooling demand, but probably this peak cooling demand is just a couple of hours per year. But if I add up the energy that I am using, it's very low. So I'm far from the annual cooling demand. It's 1 versus 10. So I think if they are reasonable people, you could get the certificate with these values. If they are not reasonable, if they say no, you don't meet the standards, it has to be 3, and you have 26. But well, I don't know. Anyway, this is what we need. Okay, so this is what we did last week. You have to compare your heating demand with the passive house heating and cooling with the passive house standards. And this week, what we have done is to calculate the number of PV panels that we need to make this building something close to a zero energy building. And we need both. We need the PV panels and we need the solar thermal collectors. At least solar thermal collectors for domestic hot water. If you want to include more solar thermal collectors to help reduce the energy that we need for heating, great. But at least this option, we need all the collectors that we need for the domestic hot water. In residential buildings, you know the amount of solar collectors that we have in this building. Maybe it's around, it might be 100 square feet maximum, even less, 50 square feet. Because in a school, without showers, we don't have domestic hot water demand. In residential buildings, it's more the domestic hot water demand is higher than in commercial buildings, unless the commercial building it's a swimming pool or a gym or something that has showers.